Greetings, everybody, and I apologize in advance for the length of this podcast. But the trade-off is there is no lab for this unit, so, got to make up the time somewhere. So we're talking about gravitation today. You already know a little bit about gravity, how we use it in our y-direction kinematics problems and our projectile motion problems. But there's a lot more to gravity than that. So here's your objectives. You're going to describe some early history of astronomy. There's going to be a big formula for universal gravitation. You're going to describe its effects on objects, and we're going to do some calculations. Good news, only one equation. Here's a little cartoon to get us started. Haha, funny. It's a big apple. It's going to fall on Newton's head, and he's going to discover gravity. Alright, so early astronomy. As far as we know, humans have always been interested in the motions of objects in the sky. They often, attributed them to, gods and stuff like that. But they also navigated by using stars and the planets. And they also used where different constellations were at the time to predict the changing of the seasons. So they knew when to plant, when to harvest, and so on and so forth. There were many early attempts to describe and explain stars and planets. Like I said, the Greeks and Romans thought that the sun was pulled across the sky by some dude in a chariot, and we all know that's a lot of crap, but, that's what they thought back then. And then, we actually started doing some astronomy, but a lot of them fell apart. A lot of people assumed that, the Earth was the center of the universe, which, it's very egotistical of us, but it's not. So here's the first attempt to understand how the solar system works, and it's called a geocentric. Geocentric. Geo meaning Earth, centric meaning centered. So Earth-centered solar system. And that's created by this Greek dude named Ptolemy, and he just basically drew it out. Like, people already thought this stuff happened, but he made a model that kind of worked with the Earth at the center. So he said, this is the Earth, here's our moon, here's the sun, Mercury. So you can see it's a lot different than, what we know is right. So Ptolemy thought his model that he made actually fit the data very well, but it was really, really ugly. He had stuff going in circles, and then stuff that's going around our Earth was going on its own circle, doing this weird loop-de-loop forever and ever. Not very elegant. In science, we'd like to find more elegant solutions. So along came this guy, and he made it more elegant. He's this Polish dude named Mr. Copernicus, and he proposed a heliocentric. Helio meaning sun, centric meaning centered. So a sun-centered solar system. And this is about 1500 ACE. So a lot of people didn't like Copernicus's ideas because people don't like, Earth-changing paradigms. Because they thought, well, how can the Earth be moving, but we don't feel it? We didn't know about inertia at the time, neither did Copernicus, but he's like, you know what, screw you, this is what happens. We also can't really see Earth's motion against, if we use the rest of the stars as a background, people couldn't explain that. It's called a stellar parallax. And his model did not fit the data as well as Ptolemy's. But that's because he just had some kinks in it. Copernicus is on the right track, but, it still didn't quite fit the data very well. Then along comes Galileo, and you should know a little bit about Galileo. And he thought that Copernicus was right because he observed the sun and Venus and the moon's Jupiter using his really powerful telescope. Well, I shouldn't say really powerful for the time, but it's pretty archaic by our today's standards. But using the data that he discovered from the sun and Venus and Jupiter's moons, he refined the Copernican solar system, the heliocentric solar system. And he's also came up with this idea about inertia. And, maybe he did that because he wanted to explain Copernicus's ideas better. So Galileo came up with inertia to help prove Copernicus's ideas. Then there's these other two dudes, Tycho Brahe and Johann Kepler. And sometime in the late 1500s, This Danish dude, Tycho Brahe, who had a really big nose and a very bad liver because he was a drunk. But he was really good at making measurements of where stuff was in the sky, and especially the planet Mars. He had a lot of data for the planet Mars, like its position at different times of the year, different dates and stuff. So Tycho got together with Kepler. Actually, Kepler went to see Tycho and tried to get the data from him. It took him a long time to finally pry the data from Kepler. In fact, like Kepler didn't get the data from Tycho until like Tycho was finally succumbing to his wantonness. But Kepler took that data and he interpreted it, and he made the solar system as we see it today. And we'll talk about more what Kepler did when we get to his laws. All right, and then along comes this guy who we know all too well, Isaac Newton. And he had the idea that maybe the motion of an apple falling to the ground is the same force that causes the moon to go around the sun. It seems pretty far stretch to think that, but he was actually right. Because it's caused by the same force, the gravitational force. And this unit's all about gravitation, so we're going to talk about it some. So Newton's idea was that gravity was a universal force acting between any two objects. So acting between the Earth, this apple, the apple and the moon and the Earth, the apple and the moon, all acting against us. Like everything's got gravity. So Newton knew that the Earth's surface, the gravitational force, equals its weight. So we have that formula for weight. The force of gravity equals our weight. And we know he used calculations, figured out G was 9.8, which we use, most of our calculations. Anytime there's a G, it's a little g. We'll talk about big G here in a second. And Newton reasoned that the centripetal force on the moon was also supplied by the Earth's gravitational force. So here we have our centripetal force, and he thought somehow that it's going to equal the weight of the moon. Wasn't quite sure how to reason it out, how to work it out mathematically at the time, but he had a pretty good idea that you can use the centripetal force to find the mass of the moon. So Newton's calculation showed that the centripetal force needed for the moon's motion was about 1/3600th of big mg, big M meaning the mass of the moon. So he was off by 1/3600th. It's a pretty big difference. Well, this is actually a pretty small number, but it made a huge difference in finding the mass of the moon. So Newton knew, though, that the moon was about 60 times farther from the center of the Earth than that apple was falling from the tree. And just so happens that 60 squared equals 3600. Where do we see this number before? Oh, we saw it right here. 3600. Coincidence? I think not. There's never coincidences in the universe. So from this, Newton reasoned that the strength of the gravitational force is not constant. In fact, the magnitude of the force is inversely proportional to the square of the distance between the objects. So the magnitude of the force is proportional to the distance, 1 over the distance squared, the inverse proportion of r squared, r being the distance between objects. So that means the further you get away, the less force you have. The closer you get, the more force you're going to have. So Newton concluded that the gravitational force is directly proportional to the masses of both objects. So it's directly proportional to the masses. So you got m1, m2, directly proportional, and inversely proportional to the distance squared, r squared. So this is almost our equation. We're missing one major piece. This formula still didn't quite work out. And that's because we have this letter here, this big G. Big G. So when two masses are separated by some distance r, then this is the force we get. This is the force of gravity. Change the color on this just to make it a little clearer. So the force of gravity equals big G times m1 times m2 divided by r squared. Now this big G that Newton figured out is a constant. It's called the universal gravitational constant. And this is its value in the SI units that we're accustomed to using in physics. So 6.67 times 10 to the negative 11 newtons times meter squared divided by kilograms squared. So we all know that a newton is a kilogram times meter over second squared. So you can work all that out. But it's convenient to leave it in these units because, see, we have r squared here on the bottom. So its units are going to be meters squared. And we have two masses up top. So we multiply those together, we get kilograms squared. And that makes, when we multiply that, all this together, we're left with just newtons for an answer, which is good because we're talking about force. Force should be in newtons. So the law of universal gravitation states that every object in the universe is attracted to every other object in the universe. Totally forgot that was going to happen. So that means the greater the mass, the greater the force of attraction. And the greater the distance, the smaller the force of attraction. So the more mass an object has, the greater force of attraction. So that means everybody is extremely attractive. You are attracted to everybody else in this world. Every single person watching this podcast is attracted to everybody else watching this podcast. Think on that. So I mentioned something about inverse squares before. Like, this is actually what's called an inverse square law. Newton's law of universal gravitation is one of these laws. And that's because the force is proportional to 1 over the square of the distance. Inverse square law. Makes sense, right? And if we graph out an inverse square force, you see how it falls off exponentially. So as the distance gets larger between objects, the force gets smaller. If the distance gets smaller, the force gets a lot bigger. So, quick little sample problem. Find the gravitational attractive force between two identical 50-gram spheres when their centers are 0.8 meters apart. So we know that our big G is that. It's always going to be that because it's a constant. So we got to use our equation. The force of gravity equals big G times the mass of the first times the mass of the second divided by r squared. Make sure you put your masses in kilograms. Got to put your masses in kilograms. I give it to you in grams, put it in kilograms. So big G times both our masses divided by the distance between them squared. And you get a force of 2.61 times 10 to the negative 13 newtons. Pretty small force, really, really small force, which makes sense if you put two 50-gram spheres next to each other on a table, you're not going to see them, magically move towards each other because it's a really small force. Now we're going to find the weight of a 75-kilogram person on the planet Earth. And we're going to find the gravitational force of attraction between a 75-kilogram person and the Earth. So to find the weight, we know it's 75, his mass, times gravity. 75 times 9.8 gives us 735 newtons. If we find the gravitational force of attraction between that same person and the Earth, we have to know the mass of the Earth. Now you're going to find in a lot of these problems, it's used like the mass of the Earth, the mass of the Moon, the mass of some other planet. All these can be found in your physics textbooks in charts. Either, I think they're in the back. I'll have to look. And you'll also find radiuses of various planets and moons also in charts in the back. So we have to know this kind of stuff. So we need to know the radius of the Earth because if a person is standing on the Earth, then the distance between him and the center of the Earth happens to be the radius of the Earth. So we need that for our r. And here's the mass of the Earth, so we just plug it into our equation. Big G, mass of the Earth, mass of the person, divided by the radius of the Earth. Don't forget your squared. And you get 737.46 newtons. So these guys, pretty darn close to each other. And they should be. They'd probably be exact if we use the entire value for the acceleration of gravity, which is a pretty long number. We just, round to 9.8. All right, so calculating the little g for planet Earth at sea level. Yeah. So we can find little g if we know that here's our force of gravity, which we have as a W here, equals that. The force of gravity also equals that. So we set these two guys equal to each other. Big G, mass of the Earth, times the mass of a person, divided by r squared. And that's going to equal mg. Now this m is the mass of whatever. It could be a person, it could be a whale, it could be, a trombone. But it's the same m as this m. So it's gone because it's on both sides of the equation. So you can find the gravitational acceleration. I couldn't believe I couldn't think of that word. So you can find acceleration at any point on the Earth if you know how far it is from the center of the Earth to that point. So as r gets bigger, our g is going to get smaller. So that means the gravitational acceleration is actually going to be smaller on, say, like, what's that giant mountain in the Himalayas? Mount Everest. So Mount Everest is actually going to be slightly smaller than 9.81. And if we go down, if we get like empty Pacific Ocean, you go down the big trench there, starts with an M, it's like Mariana Trench, Marianas, something like that. It's actually going to be bigger than 9.8. Not a lot bigger, but slightly bigger. Another example problem, the mass of the Hubble Space Telescope is 11,600 kilograms. We want to find the weight of this telescope when it's resting on Earth. And we also want to find its weight as it's in orbit 598 kilometers above the Earth's surface. So we write down everything we know. We know mass of the Earth is that, radius of the Earth is that, we know what big G is. So how do we get these answers? Well, for part A, we just can do, the weight equals mg. So 11.6 times 9.8. And that'll give us our 114,000 newtons. For B, though, we're going to have to do our Newton's law of gravitation. So mass of the Earth times the mass of, our satellite. Now the radius is the only tricky part, because it's the radius of the Earth, but we're above the Earth by 598 kilometers. So you got to add that 598 on before you square it. Not only do you have to do that, because this is in kilometers, but this is in meters. So we're going to have to convert this guy into meters. So it's actually going to be the radius of the Earth plus 598,000 meters. You got to square it. Got to make sure you're in your SI units. So this has got to be in meters. It's got to be in meters, because that's in meters. And that's in meters. Everything's got to be in meters. You can't just leave those kilometers there. And here's just something to contemplate. So down in a cave below the surface of the Earth, there is more gravity than at the Earth's surface, less gravity than the Earth's surface, or the same gravity as the Earth's surface. Now you would think that there would be more, since you're, closer to the center. But there's actually the same. Because when you're in a cave, you have all this stuff above you also pulling you outwards. So that person's standing in a cave. Happy person, he's in his cave. He's got crap above him and crap below him. So this stuff's pulling him this way. And since he's closer to the center of the Earth, it's going to be a stronger pull than our regular 9.8. But at the same time, this stuff pulls him upwards. So it's actually going to even out and come right back to 9.8. Now, it's different if you don't have anything above your head, like we're in a very extremely deep trench, then you don't have anything pulling you up, so gravity is going to be more. So people didn't like this gravitational stuff at first because it was something called action at a distance. And people just couldn't accept that, two things that are, miles, we're talking like millions of miles apart, like the Earth and the Sun, could affect each other. Because, empty space, not touching anything, like how can that happen? How can there be a force there? And they thought it was pretty spooky, and that's why they call it action at a distance. They just didn't like it. During the 19th century, the notion of a field entered physics, like gravitational fields and electric fields and stuff like that, by this dude named Michael Faraday. They did a lot with electricity, so we're going to talk more about Faraday whenever we get to the electricity part of the course. And this idea of a field was that like objects with a mass create an invisible disturbance in the space around them that is felt by other massive objects. And we call this the gravitational field. There's also a pretty cool video on gravity I might show you guys. Talks about this gravitational field and how it like bends space and time. Pretty neat. Einstein's ideas. Einstein was smart. That's why they call him Einstein. So since the sun is very massive, it creates an intense gravitational field around it, and the Earth responds to that field. So it's the field that we're feeling. So it's not this spooky, like there's nothing there. Like there's a field, invisible field, but it's still there, making the Earth do, its little orbits and stuff like that. So we got rid of the idea of action at a distance in place of the field theories. So to measure the strength of a gravitational field, we measure the force exerted on a mass. So we can find, how strong gravity is by taking that force divided by a mass, which, we're pretty used to doing because we already know that force equals mg. So we just look for g by knowing this force and dividing it by m. So near the surface of the Earth, we know that our gravity is about 9.8 meters per second squared. But more generally, where m is the mass, this big M is the mass of something creating that field, and r is the distance between the two masses. This is how we're going to find that g. So if g is the strength of the gravitational field at some point, then the gravitational force on an object's mass at that point is this, which we already know. We did this a lot when we talked about Newton's laws. So if g is a gravitational field strength at some point, measured in newtons per kilogram, which is just meters per second squared, then the free fall acceleration at that point is also g. So we can find, our free fall acceleration, we can find our force. Nothing new here. So inside of a planet, though, if you're located at a distance r from the center of a planet, all the planet's mass inside a sphere of radius pulls you towards the center of the planet. But all that mass outside of the sphere, it doesn't exert a force on you. So no net gravitational force is acting on you. So our dude in the cave, again. So we're feeling the stuff from below us. So let's say the cave's like you're here. We're somewhere below the Earth. Here's the center of the Earth. So we're feeling the force of gravity here. But everything up here is no net force because it's pulling you this way, and this way, and this way, and this way, and this way. But, remember there's also stuff like down here. Since, the Earth is a big sphere, it's pulling you that way, and that way, and that way. So we're not feeling any different because we have all this other stuff going on too. So the gravitational field inside a planet, the blue shaded part of the planet pulls you towards this guy. All these pulls you towards the center. And this stuff, everything in gray, just cancels everything else out. Now we don't feel any heavier down here because there's less mass to contend with. Because, we're taking away all this gray stuff mass. And all we're left is the blue stuff mass. So that's why we're not feeling any stronger pull. That's why we can still walk around if we go in a cave. We're not like, or we can still pick our legs up. Not like we're heavier or something. So halfway to the center of the planet, G has 1/2 its surface value. So here's everything inside. We go halfway to the center. So I guess G is affected. Disregard all that stuff I said about G not being affected. So we lose half of our field, drops off to 0 as we get down towards the center. That makes more sense. And as we go past the surface of the Earth, it starts to go down exponentially. This is very linear when we're inside. Down here, it's exponential, drops off. Never gets quite to 0, but it gets close. But if we can go to the very center of the Earth, we're going to have 0 acceleration. So actually feel less towards the center of the Earth. All right, now we're going to talk about 2 different kinds of mass. There's inertial mass, which is one we're most familiar with when we talk about how much mass we have. And, remember, if you have more mass, that means you have more inertia, and the more resistance you are to changing your motion. That's why, the linemen in football are fat dudes, because they have more mass, they're harder to move. But there's also gravitational mass, which we get from Newton's law of universal gravitation, and it determines the size of the gravitational force between the 2 objects. So anytime you've used a balance in chemistry or bio, like you're finding gravitational mass, not inertial mass. So when we're finding inertial mass, we have our regular Newton's second law, rearrange this all for m. But gravitational mass, we're taking Newton's law of universal gravitation and solving for that m guy. And this m being, whatever the other mass was, usually the Earth, if we're on Earth. So you can use this to find the speed of a satellite. Because remember when I said that centripetal force is always something else, and one of those things could be gravity? Now we have a new equation for the force of gravity. Equals, Newton's law of universal gravitation. But since it's centripetal force, it also equals mv squared over r. Now this v being the mass of a satellite we're trying to find. So this v is going to be, the speed of a satellite, not the mass. So, like I said, we're just left with these 2 parts of the equation. We can get rid of the masses because it's the same mass. This would be the mass of the satellite. This big M, little e, that's the mass of the Earth. We can get rid of one of the r's on this side and all of the r on the other side because it's the same r, the distance from the center of the Earth. And we rearrange this, solve for this v right here, and you get speed of a satellite equals square root of big G, mass of the Earth, or mass of whatever other planet we're orbiting, divided by how far you are from the center of it. So velocity is measured in meters per second, G is the gravitational constant, m is the mass of the Earth, r is the distance to the center of the Earth. And that's important because a lot of people just use the radius of the Earth, and that would be wrong when you're finding these velocities. So the radius of orbit would be from, the satellite to the center of the Earth. And that radius of orbit is going to be this chunk of distance, which is the radius of the Earth, plus however high it is above the Earth's surface, which we're going to call h. So the radius of orbit, the r we're going to use in that last equation, is the radius of the Earth plus how high it is. So what's the minimum velocity needed for a satellite to stay in orbit at 1500 km above the Earth's surface? So we use our equation, big G me divided by r, plug everything we know in. I guess I didn't work that one out. So I'm just going to leave big G as that. Times our mass of the Earth, 5.98 times 10 to the 24, divided by 6.37 times 10 to the 6. But that's just the radius of the Earth. Remember, we also have to include how high it is above the Earth. We got to convert that into meters. So it's 1,500, 123 meters. Put that in your calculator, and you get 7,910 meters per second. All right, now we're going to talk about the period of an orbiting satellite. And I'm just going to give you these equations. I'm not going to derive them for you. This m here being the mass of the Earth, so we're talking about the period of a satellite orbiting the Earth. This being the mass of the Sun, so how long it's going to take to orbit the Sun, the periods. So orbital period of the Earth, we find the orbital period of the Earth in days for one revolution around the Sun. So distance between the Sun and the center of the Earth is this radius. Mass of the Sun is that. So plug this in our calculators. We're going to use this bottom equation here. So T equals 2 pi square root r cubed over g mass of the Sun. So we plug this radius in here and our mass of the Sun in here. Big G is always big G, 2 pi, whatever. Plug that all in your calculator and you're going to end up with 365 days. But this answer will be given in seconds, so you're going to have to convert that to days. So you're going to get a huge number, all going to be in seconds. So gravity is also responsible for the tides that we experience on Earth. And every day there are 2 high tides and 2 low tides. And these tides are due to the moon. So there's a force of gravity between the moon and the water on the Earth. So the moon actually pulls the water towards the Earth. Sorry, the moon pulls the water towards itself, I should say. So why are there 2 tides? Tides are caused by the stretching of a planet. And the stretching is caused by a difference in forces on the 2 sides of an object. So the moon actually squishes the Earth into kind of like an egg shape. So since gravitational force depends on distance, there's more gravitational force on the side of the Earth closest to the moon. Makes sense. Got the moon there, moon, Earth. So the moon is pulling all this water towards it. And it's also squishing out the Earth a little bit too, making it a little more flatter. So the water comes out here bigger during high tide. And similarly on the other side of the planet, does the same thing because of the way the Earth's squished. So if we remember that the force of gravity equals big G times, our equation, there's less gravitational force on the far side, more gravitational force on the near side. So why the moon? Why doesn't the Sun cause the tides? So the Sun's gravitational pull on the Earth is much larger than the moon's gravitational pull on the Earth, which makes sense. The Sun's a lot bigger. So why the tides follow the moon and not the Sun? Now, since the Sun is much farther away from the Earth than the moon is, the difference in distance across Earth is much less significant for the Sun than the moon. So therefore, the difference in gravitational force on the 2 sides of Earth is less for the Sun than for the moon, even though the Sun's force on Earth is more. That was a big mouthful. It's basically just saying because the force is acting over a smaller distance between the Earth and the moon than the Sun and the moon. So we experience different gravitational force because of the moon. It's going to be a little bit stronger, even though the Sun pulls harder, but it's further away. So we have the r squared on bottom. So this r is smaller for the moon, which is going to make our force on this side bigger, since force is proportional to 1 over r squared. So the Sun does have a small effect on Earth's tides. So if the moon went away, if it blew up, because some stupid country wants to decide to get rid of the moon, who knows why they would do that? Kind of silly. But if the moon did disappear, the Sun, we'd still have high tide and low tide. They wouldn't be quite as big because the Sun does have a very small effect on our tides. Why does my bar keep coming up? I have no idea. And that is all. Sorry for the length of that guy.